So let's see, there's a problem. Well, let's do this one. There was a problem we did back in 15.6, I think, where we did the first step and then we translated it into polar. And I think at that time, hopefully I made the point that was basically cylindrical coordinates we did. So for example, just to catch everybody up, remind me about polar coordinates conversions. What are the conversion formulas for polar x equals? That's crazy. And now we'll say z equals z. Whoa, shit. All right. Believe it or not, that's the official. That's how you convert. And then you go backwards. So this is if you have polar, this is how you convert it back to x, y. Or if you have x's, you want to convert, you want to change them into polar, then you put this in place of the x. What if I have rectangular? R squared, of course, is. And then tangent theta. Y over x. Y over x. And then z equals z. Gotta like the symmetric conversions. So again, I really hope everybody gets this. It's polar with an added height to it. So you could be integrating some surface over a circular region in the xy plane. You could do that with triple integrals. You really wouldn't have to. Let me see. I think I have an example. Yeah, all right. Now, hopefully it's really obvious that this is just screaming to be put into circular kind of stuff. And this is screaming for polar at least, but now I can see this as truly cylindrical because it's got this extra third integration in the middle. It's the height component, right? So it's not even going to be a volume. How do I know it's not going to be a volume that I end up with? What do you need inside a triple integral if you're going to end up with a true volume? 1. So this is actually evaluating some function over some volume region, right? So again, it could be density, it could be flow of something, yeah. Okay, maybe flow of heat, flow of water, whatever. Through some 3D thing. Flow of electrical fields, magnetic fields, if you guys are experiencing that right now. So take a minute and see if you could change some of this into polar. Let me try to catch up to you guys here. Hopefully a few things are really jumping out quickly. What is this here? R. That's just R. Square root, so it's R. Of course, inside it's going to be R squared. All right, so let's see. This is going to become R squared. What does dz, dy, dx become? So then it becomes R, and now you just throw a dz in there, right? Because I didn't have that third inner integral before, and now we're adding that height. So normally it's r d theta, and then you sound as a little Swedish or something, r dr. But now I'm going to throw the dz in there. So now it's going to be r dz dr d theta. So what does z go from to? R to 2. And what does r go from to? What's it look like in the, what do these together make in the xy plane?
Circle.
Circle. Yeah. Whoa, pretend like this is a circle. All right. 2, -2. So it makes sense the x is going from -2 to 2. That matches up with what it really is. Be really careful about, it's just like translating from one language to another. If you just go word by word, sometimes it won't make any sense. So you guys know what I mean. If you use Google Translate to go into your home language, and you're like, what the shit is that? You don't want to go straight from here. That -2 equals -2, and it doesn't make any sense. You've got to sketch it out. And then kind of start over again, really. So what does r go from to? 0 to 2. And what will theta go from to? 0 to 2 pi. Does what I just said make sense? You can't take each integral and just translate the limits. Because all of these two together define a region. You have to graph that region, and then really you have to start over with the new. It's not as bad as it sounds, but hopefully you see what I mean. You can't just go from this to the answer. Now, does that look difficult to do? No, do it real quick. Some of you guys forgot this poor little dude, which made the integral impossible to do, but somehow you found a way to do it anyway. I appreciate that sense of optimism and confidence, but no. So let's see. This is dz, of course. So you're not integrating r cubed, truly. You're integrating constants, so it's r cubed times z. And then z will be 2 minus r. Is that cool when you put the limits in? So it'll be 2r cubed minus r to the 4th. Some of you guys have picked up on the fact, you don't have to do this, but the book shows, of course, this is all r, so theta doesn't matter, so it's just going to have a multiplier of 2 pi on it. Very often if if there's a missing variable, it's just going to be a multiplier in that case. Because when you integrate, there's going to be theta on the back end, so it's just going to be multiplied by 2 pi minus 0. So this will be 2 pi times
R to the fourth.
yeah, r to the 4th over 2 minus r to the 5th over 5, evaluated from 0 to 2. And then whatever you get. I think you should get 16/5 pi, right?
Yeah.
That's what I got. All right, cool. Lock it. So polar is the one that introduced that requirement of r. So just because I throw a z in doesn't mean this little required r goes away. Just the z gets slapped in there. Because I normally consider the z to be the surfaces that I'm going between. All right, maybe. So cylindrical is really not a lot to it, thankfully. If you understand polar, then cylindrical is just like one little step away. Let's see. Here, try this one. Give me one real quick. If you got your book, it's number 23, page 1084. Funky to say. Fifths. 8/5, 16 pi over 5, right? Yeah. All right. Let's see. So for the booklets out there, $23 there. Neato. So real quick, right here, this is a cone. Kind of makes sense because as you move away, so what does it say? Z equals square root of x squared plus y squared. As you move away from the origin, of course at the origin it's 0. And in any direction as you move away from it, it's going to get taller. That's exactly what a cone does. All right, the further you get away from the origin, the higher it is. So it's just going to be a cone. So find the volume enclosed by the cone and the sphere.
just in case somebody's not really sure where to start. Who out there knows the first step? What are you guys doing? What's the very first step you need to do? You need to see where those two things intersect. There you go. That's a quick way to say what I think hopefully somebody out there said. You need to see where they intersect. It kind of makes sense. The cone's going to start at 0 and kind of open up, right? And the sphere is going to be over that. So it's going to be this neat ice cream cone looking thing, right? The sphere part plopped on top of the cone. Right? I need some ice cream. So if I find where they meet, that's what I was saying before. That's the widest part, and that's going to be you want to plop that into the XY plane. That's going to be your input region. That's going to be your points that actually have outputs on those surfaces. So you have to find the intersection first to help figure out what the limits are going to be. Oh, yeah, actually for this one, you wouldn't even, why would you not really need that third interval in the middle, to be honest? Because they're asking for a volume. So the interior would be 1 with triple intervals, or it would be the difference in what would be the limits on the inner interval. Does that, it's going to lead to the same thing. So I showed you an example of some Math 180 stuff you did with 1 interval. You could actually set 2 intervals up for, but the limits would be the difference in the functions inside anyway. Ooh. So the interior of the 2 intervals would be the difference in the surfaces that we're talking about. That would be the limits on the inner interval. Let's see how that less words.
That's 24.
Huh? Oh, I like it. What you meant to say was that's one more than what I'm doing. Then that's true. All right, let me make sure everybody's got like the first step going. Now you could either work with it the way it is, or you could actually go ahead and translate it into polar anyway and then use those. It actually makes a much nicer equation, but either way it should be pretty simple. If you throw that bad boy in here, then you get 2x squares and 2y squares equals 2, so you get x squared plus y squared equals 1. All right, so they intersect, the cone opens up and the sphere opens down, and they intersect on this circle of radius 1. Is that cool? Or you could say, all right, well, z squared equals r squared, and it's got to be on r squared plus z squared equals 2. You basically get the same thing. You plug that in, you get 2r squared, you get r equals 1 at the end of the day. Either way you look at it. Either in your face, or you got to think about it for a second. Oh, yeah, radius is 1. Okay, keep going. I want to make sure everybody's got that step down. Yeah, since it doesn't chop any slices, right? It's going to be complete. It doesn't say some part of the sphere. It says the whole cone and the whole sphere. Yeah, 0 to 2 pi. So anytime they say something like in the first octant or something, that's going to automatically mean it's going to mean that your theta is not going to be from 0 to 2 pi. And of course, in that case, it's going to be from 0 to pi over 2. Yeah. So look for those kind of things. Look for anything that chops a piece of it, and then your theta is going to have to change accordingly. So what is, let's see. Let me see if you guys, I don't need that third integral truly. So what am I going to put inside? It's going to be the difference of the surfaces. What does z go from to? What's on the top? Going to be the ice cream, the sphere. And what's the equation of the sphere? Z equals square root of, I don't have to put a negative there because I know it's the top part, right? So that's the sphere. So that's going to go where on the integral here? I'm sorry, where's it going to go inside the integral? I don't have a triple integral. It's going to go first, because it would be on the top. It would be the top limit. All right, so square root of 2 minus r squared. Minus, and of course, the other thing for z is, yeah, z equals r. You got to love that shit, right? The other surface was this cone, and z equals r. So it goes from the sphere, square root of 2 minus r squared, to the cone, r. You guys all right with that? You guys okay? So you guys, I love it. These pained look on your faces all the time, then you never ask anything. It's like, I can do nothing for your pain if you say nothing. Okay. You can always increase your pain, that's for sure. And what does r go from to? R, of course, goes from to what? 0 to 1, we already said that. And of course, like somebody just mentioned, theta is going to go from 0 to 2 pi. And of course, what's nice about this, if you forget this first thing would suck quite a bit. Since that's there and you distribute, that first thing is just going to be a u sub. I love it. So finish that out. You know, if you really need to, you can split it up as the difference of two double integrals. So you can, because only part of this needs u sub, right? So that sometimes messes people up. You don't want to put a 1/2 in front of everything because this guy don't need it, right? That's where people make a little mistake. But if you do, you just got to put a 2 there. It's all right. It'll work out that way too. That's how I did it. Yeah. Yep.
Why does z goes from 2 minus r squared to r instead of going from r to?
So z equals r is which thing? Z equals r is the cone, right? Z equals r is the cone. And z equals square root of 2 minus r squared is the sphere, the piece of the sphere on top. So yeah, z is going to go from the cone to the sphere. Yeah, I like it. There's not a damn thing wrong with sketching something. That's not 3D, but that's a useful sketch for me, right? So it's so what I would do is this. I would say I need a -1/2. Do that if you want to. If you don't want to split it up into two intervals. And notice also that what's going to happen with the 0 to 2 pi thing, it's just going to, there's no theta dependence inside, right? So it's just going to be a multiplier. So -1/2 times 2 pi, I got a negative pi out front. And now I got to figure out this inner integral. Of course, you don't have to do it the exact same way I'm doing it, right? I mean, we should end up in the same place, hopefully. All right, guys, so here, if you let u equal the inside, du is the outside, right? Cool. So then you'll end up with square root of u to the 1/2. When you integrate that, you get the integral u to the 1/2. Yeah, 2/3 u to the 3/2. So you get 2/3 times 2 minus r squared to the 3/2. And of course, when you integrate this, yeah, 2r cubed over 3. I'm going from 0 to 1. And here's where you got to be really careful also. I mean, you've run into this enough so far, hopefully, and before this class, 0 actually does something, so your poor little 0 dude. So if I wanted to, I could take a 2/3 out. Is that cool? Negative 2 pi over 3. And then when I throw a 1 in, I'm going to get 1 plus 1 minus 2 to the 3/2. I like it. And then, of course, 0, right? So, I mean, now you get, let's see. When you distribute this, you could do 2 to the 5/2 pi over 3 minus 4 pi over 3. 2 times this, and that times this makes it positive. You can write this whatever way you want to. Just don't write it as a decimal because that would take you for the rest of your life, so don't do that. Cool. All right, maybe. All right. So again, we've basically done cylindrical before today. It's just that it makes it a more complete package because now I'm going to do stuff where I do need triple integrals. So we need to start fully with cylindrical to do it. Okay. So let's talk about spherical. So I think I said this to you guys before. I gave you a little bit of an idea about spherical. So with polar, it's in 2D. And with polar, it's you tell somebody, so here's 0. You tell somebody the angle, so you tell them where to look, and then you tell them how far to walk in that direction, right? That's what theta and r are. So with spherical, I start with polar, really, but I have to consider the end point. So let's say I want to get to this point here. All right, it's right there. So I want to turn this much. So theta is going to be the same old theta, thank God. Theta is going to be in the xy plane. Are you guys with me?
There won't be any R, though. At least not the way we're doing it. It's different things did differently. So I have to turn so much theta. I then have to turn so much away from the z-axis so I can face this thing. So this is going to be phi or phi. Either way, I know. There's some stupid jokes in there, but right? So the angles are theta, the one we know. The new angle is going to be the angle with respect to the z-axis. So what do you think it goes? 0 would mean that the point is going to be on the z-axis. What's the other angle that would be on the z-axis? Pi. In fact, how far will phi go from 2? 0 to pi. I don't need it to go to 2 pi, because if I wanted to go back there, I would just turn. Theta would get me to turn the right way. So I only need phi or phi. Again, it depends on how I feel of which way I'm going to say it. I only need that to go from 0 to pi. Right? Because then when you turn this way, no, it's always that less than 180 degree angle that I'm measuring. Okay, maybe. I got a handout, by the way, thank God. Let me show you the picture that's going to be on the handout that I don't want to give you yet because it's got all the answers that I want to talk about. So there's everything I just said. So you want to tell somebody you got some point that you could define with x, y, z, right? Totally. All day long, you can define that by x, y, z. But now I want to use these funky things. We're not going to use r anymore. The three-dimensional analog of r is rho. And I like that this book uses rho. It's another Greek letter, rho. Because r, I was brought up to think that r is in the 2D. Right? So rho is its own thing. Because I want to be able to define rho in terms of r, or vice versa sometimes. So I need them to have separate symbols. Some books use r there also, which doesn't really make much sense to me. So you have a certain distance out. Now let's see if we can make up some conversion formulas here. And this is not going to necessarily help. It's just going to bring back old nightmares. But this is the submarine problem, basically. This really is. So, since theta is between x and y, theta is going to differentiate between x and y. Phi is going to differentiate between z and xy plane. What the hell do I mean by that? So what's the z component going to be? That's got to be the easiest part of this. What's z going to be in terms of all this stuff? So z is not equal to phi, right? Because if I keep phi the same but increase rho, then z is going to increase. Are you with me? So z isn't equal to phi, because if I keep phi the same but increase or decrease rho, z goes up and down accordingly. Okay, so what must it be then? I just made a little triangle, didn't I? Love some of you looked in your faces. Not that bad, guys.
Rho cosine?
Yeah, it's just rho cosine. So z is going to be rho cosine phi. That was your climbing or descending for your submarine. Was that? And then what's left over to be here? What's this going to be? If that's rho cosine phi, this must be rho sine of phi. No, Jeff, get ahead of yourself. Rho sine of phi. And then that is an expression that is how long this shadow is, right? And of course, how am I going to get the x and the y pieces? I'm going to have to take that shadow and break it up into two parts, yeah. I love it. All you guys are searching for some technical numbers. Break it up. I want to break it up into the x piece, the y piece. So this is now rho sine phi. So what's the x piece going to be? Rho sine phi cosine theta. So the y piece is going to be
Rho sine phi cosine theta.
yeah, y is going to be rho sine phi sine theta. Whoa! All right. So let me give you this handout here so you don't go insane trying to figure out how to write all that down. On the front of this is the picture for the cylindrical, on the back is the spherical.
Well, the angle's actually.
No.
So the back of this is the spherical. There are the formulas for going between the two. Notice that since theta lives in the xy plane, the tangent theta equals y over x is still valid. That's kind of awesome. Theta is the two-dimensional angle measurement base. It's in the xy plane. That's awesome. This one might be a little bit freaky, but it's just the reverse of this, right? Cosine phi equals z over rho. It's crazy. So let's do this. I think this would be very simple. You guys should be able to do these. I just put them down there just because this is the new shit, really. So let's do these. You guys do 1 through 5 there on the back. Let me know if you need some help.